I need to unmute us. Hello, everyone. Happy Monday
Hello.
for a change, right? It's not Wednesday today, by the way. And yeah, anyone that's here with us today, we're happy to welcome back our very good friend and magnificent artist and TD and coder and everything else and mustache, Dominik Ruckli. How you doing, Dominic?
Thanks, I'm doing fine.
Good, good. And yeah, today is our last installment from the Node series for the time being. Now, make sure you go and check out the Nodes tutorials I'm preparing for you on this university, which I'm going to show you in a second. So let's go through the housekeeping and let's get this going. Let me put this on the full screen and I'm going to copy and paste this in the chat over here and click on that link and it will take you to this page over here. And you get all the links, including the Ask the Trainer question form. You can go to the Maxon events page. All the cool stuff we are doing at Maxon, all the events are presented here. Of course, links to the Maxon Training Team YouTube channel, which is the only channel that hosts these videos after you've watched them live. So if you want to watch the reruns, with comments and timestamps kindly provided by a very good friend and mentor, Dr. Sassy. Please go to the Maxon Training Team. But currently, we are streaming on both the Maxon Training Team and the Maxon YouTube channels. Do not forget to go to the Maxon ZBrush channel and check out all the fantastic tutorials and presentations from these amazing artists. Grab your iPad, sit on the couch, and sculpt. Finally, you can go to this university, and these are the videos I've been working on. And just go and check out the little list of stuff. I think they're in the reverse order here, so this is going to be the first one you're going to check out. But in any case, I'm preparing more, and we're going to add a lot more information on this as we go along. The first tutorials I've made are mostly with the particle node modifier to get you up and running. And then I've done a few things which have to do with creating splines, arrays, and various other things. Excellent. Of course, if you have questions about how this is supposed to work or anything that relates to the stuff that Dominic is making, just make sure to ask your questions. So having said that, I'm going to be looking at the chats. If you have any questions, please preface them with this, with question. That's number one. Number two, don't forget, there's going to be a link below this video that has the project files, and Dominic has provided all his scenes for you to download and go and look around, snoop, and find out how things are done. And what else do I need to say? Subscribe, press those buttons, and do whatever you need to do to get notified and help the algorithm push our videos to more users. Fantastic. Anything else I need to say? And again, please preface any questions with question, and I will try and get to it with as fewer disruptions to Dominic as possible. So here's Dominic's screen. And Dominic, the floor is yours.
Thank you. So yeah, hello everyone. Today, maybe as you already see here, we dive in again into nodes, but this time we go a little bit more advanced. So last time we showed you, and also in Jonas' stream, we showed you how to do a little bit of modeling with nodes. So in this stream, we go a little bit further. So I like to show you, we have 4 parts. So we built 4 little setups. And in those 4 setups, we make use of 2 very handy. They're a bit scary, but that's why we are doing this stream here. So with the 2 nodes, one called the loop carried value and one is the memory node. So what we do first is actually the main image here. We do a noise inset mesh. So I'll come to this. I'll also show you some videos. where I explain the loop carried value. Then we built the generator together. So we built this little ball here. This is actually the same principle here, this head here and this ball. So we built this ball, so a little bit an easier setup. So, and then the next one, we built a stacking generator where we can stack boxes or whatever on top of each other, depending on their Y size. This will look like this. Then we start with the memory node, and we build a little super simple extrusion solver. So this will be animated. So this will look like this. And then for the last part, we build a setup where we can attach an object to the closest point of another moving object. So this is what we do at the end. So this is the most complex. It looks a bit simple here, but there's a lot of stuff in there what could be very interesting, and also a setup that could be useful in a bigger setup. So we will see this at the end. So then I think we can jump into Cinema and start with this noise inset. So let's go to Cinema, and maybe let me show you the little video first, what we are going to do. So let's open this one here. So, and here you can see we have a sphere here. We are insetting the sphere depending on a noise value. So every polygon that we have has a different inset. So, and then we split those two geometries. So the inset, the geometry, and the rest. And then we built this blobby eye-looking ball here. So let's jump into Cinema, and let's start by preparing some geometry. So first, we need a ball with kind of an interesting geometry to inset the geometry. So let's take a sphere. Let's show the geometry here. Then let's make it a icosahedron. Let's add some additional geometry. Then let's place this under a polyreduction. And maybe something around this. And now we want to build a dual mesh here out of those triangles. So this is here a little trick. First, put it under a connect, keep on weld, and then under a connect, add a bevel deformer. So let's click Shift, and then we have the bevel deformer here. Switch the bevel deformer to points, then to proportional, and then a little bit up. And now we have here the dual mesh here. This looks a bit like a honeycomb. This is now our mesh we like to inset depending on a noise value. So first we have to bring here our geometry into nodes. So we're building a generator. So let's press Shift C and search for nodes. And we like to use the nodes mesh because we want to manipulate mesh. Then let's place here our sphere under the mesh. Let's open it. Let's put this down here. And then we have to bring in here our child geometry. So right click here to the inputs, say add input, and then we have here this object child. Now we have here our first child here, so our sphere with the matrix, geometry, and so on. So let's grab the geometry, put it to here. And now we have here our geometry back. And now, of course, we like to inset those polygons. So let's use an inset. Then press Q to output it. And now we see we inset every polygon here, here with 20% here. So we can define here how much you like to inset. And then there is also an inset variation. So where you can randomly inset. So, but this is actually not what we want. We want an inset depending on a noise value, and also this noise should move. So we have this blobby ball. So let's do something else. Because we can't plug in here a noise or something, we just can inset every polygon all together, or we can use the selection string. So we can maybe say, just do it on the first polygon. So we type in here 1. Where is it? Let's search for it. Where is the first one? It's down here. So this is our first polygon. And then for this polygon, we can decide how many we like to inset this. And now it would be great to do this for each polygon individually. So we can define for each polygon an individual inset. So that's where the node, the loop carried value will come into. This will be very handy for this. So let's bring in the loop carried value. That's called loop carried value. And this node, you can dive in and do stuff inside. So it does what it says. It is a loop, and it can carry a value over each loop. So here with the curly brackets, as we already learned, here we can start iterations. So we can define how many loops we have. And on each loop, we can carry a value to the next loop. So we can manipulate something and bring it to the next loop. So what we like to manipulate here over each loop is actually our geometry, so our sphere here. So we have the initial value here at the moment, it is in vector. So you could add as many as you want. So we need just one value now, but not a vector. We like to have geometry. So this is our geometry. So let's input our geometry into the loop carried value. Let's take the inset and bring the inset into our loop here. Then bring the geometry to here and then to the output. Go back. And now we have still the same. So what we have to do now is to define how many loops, because how many loops do we want? We want for every polygon, an individual loop. So we need some information about our mesh. So how many polygons? So about the polygons, there is a node called polygon info. So type in info, and then there is the polygon info node. This is super handy. It gives us all the information about our polygons here. So the center of the polygon, the normals, and also here the polygon indices. So from 0 to how many polygon we have. So, and this we can use to iterate over our over our loops. So let's iterate over our polygon indices. So we'll use an iterate collection for this. Oops, iterate. Where is it? Oh, iterate. So I have to spell it right. Plug this in here. And now we have here the index and the elements of this array. So this is an array with integers. It's actually just a polygon indices. So it is from 0 to the count of polygons. So the index and the elements is in this case the same. So we can plug in now our curly bracket to the other curly bracket. Let's go back here, and we could already see we have now, I'm not sure how many polygons we have, so, but now we have here an inset on the first polygon again and again. So let's dive in here. So the inset is, we have here the selection string for the first polygon. So it loops always over the first polygon, but we actually like to switch in every loop. We like to switch then the selection string here. So, and also we like to change in every loop the inset. So also bring out the inset. So control onto this little circle here. And now we have the selection string and the inset exposed. Let's bring them outside of the loop. So put them here, add them in as input. Let's go outside. And now let's add the index here to our selection string. And now we can see We have an inset for each polygon. So change this here. At the moment, it is pretty much the same. We have an inset for each polygon, but with the value of 20. And now it would be great to inset every polygon depending on the noise. So let's bring in some noise. Let's type in noise. Then there is this handy node called sample noise. This noise needs a position value, so where to sample the noise. And of course, this will be here our polygon center where we like to sample the noise. So let's take the corresponding center. So let's use a get element. Let's plug in here our centers. Then put this up here and let's pick the corresponding center and add this to the noise. And because the inset is in value is from 0 to 100%, so this is equals to from 0 to 1. And here also the result is also 0 to 1, so this matches perfect. Plug this in here. And now we can already see we have different insets here. So this part here we have not a lot of inset, and maybe up here we have a lot of inset. So maybe let's change the noise a bit so we can see it better. Here on the noise we have the scale value, then the noise type, and also the seed value. So this is maybe something we can expose, so we can use it as a parameter. Let's bring them out here as parameters. Let's make a nice interface here. So the scale, the noise type, and the seed. Let's bring them into here. So this is looks proper here. And now we have it here on our capsule, the scale, the noise type, and the seed. So the noise type here is normally this is goes in the opposite as and you have a high number here. Then the noise is pretty small. When you have a very low number, the noise gets bigger. So when we type in 0.02, something like this, we can see it better. We have here now areas where we have less inset, and here areas, so depending on the noise, where we have a lot of inset. And then, of course, we like to animate this. So on the sample noise, there is this time parameter, so we can expose this time parameter, and there we can plug in a time node, type in time, and because we like to change the speed, so we could just take the scene time, plug this into here, but we like to multiply it first. Now we bring this into the time, and now we can use this as a speed value. Also bring it into here and go to the capsule here and maybe say speed of 2. Let's check. So, and now we can see it changes here depending on our noise, the inset, and then we are close to finish for the last part. We like to split, as we showed here. Let me show again here. We like to split the center polygons with from the rest, so we can make those eye-looking shapes here. So, oops, let's bring this back here. So we need a way to split this stuff. So we can do this with a split node. Use a split. It's also something that we used in the last stream a lot. We plug this in here. And now we need a way to split the centers here. So the centers here, they keep the same integer, the same polygon index that we have here. So we can use those, this array of integers as a selection string. So not as a selection string, sorry, as an actual selection. So when we right click here on the split and we go to add input, there is the selection string. So this is here, so that we can type in the name of a selection or want or numbers or stuff. But there's also a normal selection. So there we can plug in arrays. So bring this in here. And here we can plug in arrays of Boolean values or also arrays of integers. So when we plug in an array with integers, we select just those integers, just those indices that we have here inside this array. So we can use this here as selection array, plug this in here. Let's check, let's output this, and now we can see here we have just the centers, and here in the remainder, we have the rest. So great, let's make some selections. So let's store those. Let's use a store selection. Let's store here our centers. Like say polygon, let's maybe say center, and let's store all polygons. Do the same for the rest here. Maybe let's call this rest and also all. And now we have to connect them together. Let's connect it. And then let's bring this to the output. And now we can see here on the nodes mesh, we have now two selections, the center selection and the rest selection. So let's make two materials. Maybe let's make one red, the other one maybe something like this. Let's place them on our capsule here. Then bring here the center selection, and to this one the rest. Here we go. And for the rest, because we like to have this more like this, it's not just a surface, so we have more a volume to it. We can use a thicken here. Let's add a thicken, and at the end, let's add a subdivision surface. Let's have a look, and then let's press play. And you can see it's not the fastest setup because we have to do the loop over and over, but it gives a good idea what you could do with the loop carried value. So now, of course, you can switch the sphere here. Maybe let's use a torus, bring in a torus instead of the sphere. And now we have it here on the same on the torus. And then, of course, you can play around here with the settings, change the noise, the seed, and so on. Yeah, and I think that's it here for the first example already. And then maybe I will ask if there are some questions.
Wow, that's fantastic. We have a couple of questions. Lisa asks, question, Dominik, how do you learn about each of so many nodes offered by Cinema 4D? Do you explore them in your free time, or is it that you use them a lot in your projects? Any recommendations for us?
Yes, it's a little bit of both. Of course, first I did this in my free time because I like to do stuff like this. If it is in Cinema, Houdini, or all other software, I like to do those procedural programmatic stuff. And because Cinema is my favorite software that I also use the most in my client projects. So that's why I was super happy about the node system. So some tips that I can recommend is first, all the nodes there is a documentation about the nodes. So you can, if you like to access the documentation of each node, an easy way. So when you think of, okay, we have here the store selection, then go on one of the parameters and maybe say here and then show help. And then the help pops up, and then you see here have the save selection. Then you have some description about the node. Sometimes you also have some scene files also, so it's super handy. And then of course here the description of all the different parameters. Here the input. So you have here the description of all the parameters, and that's actually the best way also in other software to learn about the different nodes, how you can use them. And as you see, Maxon also provides here test files that you can check out. And there are also a lot of test files already in the content browser. There you can, maybe let me search for them. I think the other scenes, I'm not 100%, I don't use them a lot, but there are, maybe in Noseman, you know where they are, example scenes. I think there's here.
I don't.
See notes here. Here we go. Then it's under example scenes, features, and then C notes. Here you have also a lot of example scenes that you can check out. So everything built with notes. And then for the last, what I can recommend is, of course, the C notes here that Noseman made, the new one. And then there's also a good series from Core4D. They do a lot of basic tutorials. So if you want to start to learn nodes, they start with all the little details and all the super basic stuff, and then they go into advanced stuff. So there you also can learn a lot of stuff. So that's my recommendations, where to start and what you can use to learn C nodes.
One thing I want to add to this is there are two components when it comes to this kind of programmatic. One is to learn the software-specific tools. It's very important. But the other one is to understand generative, 3D and, how to generally program things. And what I would suggest is, if you're not in the habit of watching various YouTubers that do coding in real time, a nice one I like is Coding Train.
Yes.
He's quite good at showing how you would approach something. I think it's Jason Lang.
Sebastian Laub, maybe.
Sebastian Lang. Yeah. That is quite good. But generally, if you start searching quite high-profile channels that show how to code, even if it's Shader Toy making shaders, I've actually created some experimental setups using open shader, what's it called? OSL, open shader language. Not the language itself, but the algorithms from that, in order to create a spiral deformation of something, for example. So any resource that shows you how to do things programmatically, it's going to advance your ability to solve problems using nodal systems. And it doesn't matter what nodal system you're using, whether it's Fusion or Nuke or any other 3D software or Cinema 4D scene nodes. The underlying concepts are going to allow you to gain knowledge to solve more high-end problems. So the last thing I want to comment about is, Lisa says, Dominik and Noseman, you are both like scientists. Not exactly, because science is based on the premise that you say something, it's probably wrong, then you optimize it, everyone jumps on you, and then you prove that if they were wrong. We don't have these issues with Dominik. We're always right. So we're kind of anti-scientific. We're more like wizards, as someone said. I would take that. We're, what was the Asterix wizard's name?
Miraculix.
Yeah, the druid. That's what we are. We are druids.
Correct.
Okay, I'm gonna hand the lantern back to Dominik and put it on full screen.
Yes. Okay. So that was it for the first example. So let's go back to the presentation and let's have a look what we're gonna do next. So next thing we like to do is this stacking generator. So we like to stack one box on top of each other, and this is also loop carried value is also perfect for this. So because we can't stack all boxes on top of each other at once, we also have to do the second on the first and the third on the second. We have to do this one after each other. So for this is the loop carried value is perfect. So
a little thing,
yeah.
just to jump in. As I replied to someone that was asking, I think it was Sorab, that asked me, one of the tutorials I'm recording now for the second set of node tutorials is going to be about the loop carried value. And then we're going to do one with a memory node and so forth. So we are going to be providing tutorials on how the loop carried value works. So that's what I want to say. Thank you.
Great. Okay, so let me have prepared here a little file so we can start from this. We don't have to build everything from scratch. So I think it's this one here. Yes. Let's jump into Cinema. Okay. Here I have, let's deactivate the cloner. I have these 3 boxes here. So I have them from Quixel and I put them into a cloner. I think I made 8 clones. So we have 8 boxes here. And then I added some random rotation. I think they are also, yeah, the clones are distributed randomly. So they're cloned randomly, not distributed. So now we have here 8 boxes that we like to stack on top of each other. So how do we gonna do that? For this, I maybe show you a little bit of explanation first. I made here a little file where we can see it from the side. So we have here 3 boxes. So the box 1 here, the yellow one, the purple one, and then our pink one and the blue one. And we have they're all here in the center. Now we like to stack one on top of each other. So how do we do that? So maybe focus here on the first and the second one. So what information do we need? We need the bounding box information of both of those boxes. So let's use a doodle here. So from the first box, we need the bounding box information. So from y plus, so we need to know the value here. The top is, how should I say this? The point that is in the maximum has the maximum number of the y component. So this is around here. So this is around, I would say here, 40 centimeters. So this is the maximum bound of the first box. And then we also need the minimum bound of the second box, of this one. Maybe let's make this blue. So the minimum bound is here. So, and we can already see the minimum bound here from 0 to here. This is, I think it's exactly 100 here. So this is minus 100. And you can already see this together is the amount we have to shift or transform here our second box. So this box, you have to move this up here. So when we move it, this 140 centimeters, we can stack the second box on the first one. So what we have to do now is we take the maximum bound here. So let's maybe say the max bound of the first minus the minimum bound of the second box. So when we write here 40 minus 100, then we get 140, and that's the amount we have to shift this box. Voila. And then when we did this with the first box, the second box on top of the first, we have to do the same here for the third one. So we have to take the maximum bound of the second one, so we can already see where this is going. So when we paint, paint here, come on, the doodle, let's make a new one here. Here, from this, for the second box, the maximum bound here, and from the third one here, the minimum. So this, and then we do the same. So we see the third box has to go here. So we have to move it this distance here. And that's it. And that's what we have to do inside the loop carried value. So enough explanations here. Let's jump back to our file here and let's prepare our nodes generator. First, we can't plug in a cloner directly into C nodes. We have to collect all the geometry inside of a connect. So deactivate weld, and now we have here a single geometry, and this geometry we can bring into nodes. So let's use again a nodes mesh and make this as a child here. Let's open the nodes mesh, maybe call this stacking generator, and then the same. Let's make an input here, object child. Then we have here our geometry. Bring this to here. You can see we lose the textures, but because we have here for every box, I have here a selection that contains all polygons. So when I double click here, there's 1, 2, 3. So those selections, we can collect them and they pipe through the whole node system here. So when we maybe convert this here, like current state object, we can see here we have those selections. So great. And let's take our materials and bring them up here. And now we have our materials back here on our boxes. So at the moment, this is just one geometry. So we have to split our boxes. So we have each box as an individual geometry. So we can do this with an explode. It's called explode mesh islands. So we plug this into here. And now we have here an array with geometry. So maybe let's check, get element. So when we get the first element here with the index 1, we have the first box and so on. So we have all 8 boxes here in this array. So great. So what we have to do now, we have to prepare first our arrays before we jump into the loop carried value. As we said, we like to start with the first box. So we need an array with just the first box. So we say get element, let's get the first box, and then let's build an array. And the type is geometry. We just want 1, then plug our first box into here. So now we have here an array with just the first box. And now we need the opposite because we want to iterate over all our other boxes and to stack them onto the first box and put them in this array here. So we have to do the opposite. We use an erase elements. So we take this array here, plug this in here, and then we say remove. So erase elements. We like to erase the element with the index 1. So we remove the first box. Now we have here an array with all the other boxes. So here is the first box with the index 0, and here are the other boxes from index 1 to 8. Great. So now let's bring in our loop carried value. Here is our loop carried value. So what is our initial value? Our initial value is the array. So at the end, we want an array with all the boxes in there stacked. So we bring in here our first array here. So you could switch it here, the type. You can also just plug in here the array into this type. So you can see here, this is the actual value. And this is the type definition of this value. So when we plug in here our array into this type, then we get this type of node. And now we can see our initial value here switches to an array with geometry. I think now we can delete this, and now it is set. Here we see, okay, it's an array with geometry. So perfect. Let's bring in our first our array with the first box. And now we have to define how many loops do we like to have. So we need a loop for every additional box. So we can iterate here over our additional boxes here. So let's use an iterate collection. Let's iterate over all the other boxes. So we have here all the individual boxes, and then we can use this curly bracket here to bring this into the loop. And now we have 7 loops, so for all additional boxes. And we bring in also the geometry of each box. So, and now we have here the loop prepared, so that's perfect. And inside this loop, we're gonna do what we discussed here. So let's jump into the loop carried value. And first, here is the initial value with the first box. So we need the first box first. So we can use with a node called pop element. With the pop element, we always get the last element of an array. So when we are in the second loop, we get the also the second box. So we get always the last box. So as we discussed here, when we are working with the on the third box, we need the last box in the array, and this is the second box here. So to do our calculation. And of course, here I need our current box, and then we need those bounding box values, as I already discussed. So let's use a node called bounding box. Here is the bounding box node. Then we plug in here the first box, and this here is our second box. And as I said, we like to stack it in the y direction. So we need from the first box, we need the maximum bound. From the second box, we need the minimum bound. So we have here the first box. Here is the maximum bound, the y component, and here is the minimum bound of the second box, also the y component. Now let's use a subtract, as we did. Here's the subtract. Then say the maximum y component and the minimum y component from the second box. And now we have here the value, how much we like to transform the second box in the y direction. So we are close to finish. So let's use a transform geometry for this. We like to transform our second box with here in the translation in the y direction. Plug this into here. And now for the last step, we have to add here our transformed box into our box area, into our array with the geometry inside. So we can use an append node for this. So we like to append our box here, our second box, plug this in here, and then we like to update here our array. And now fingers crossed, I hope everything works. And now we have here an array with all our stacked boxes. Let's check. Use a connect. So let's connect all the boxes together. And we can see, here we go, all the boxes are stacked on top of each other. Now for the last step, when we go to a side view, we can see we have here a little gap sometimes because the boxes are not perfect straight. So it would be great to build kind of an offset parameter here for our capsule. So let's go into loop carried value. And here where we calculated our offset value, let's add here a little amount here. So I'll use an add node. Oops. then bring this out here of the loop carried value, and then let's make a parameter here, maybe call this offset, and then right click, go to the edit part. So let's define here our parameter. So the unit is meter, default value 0, step maybe a small step size 0.01, and then maybe a slider from maybe -2 to 2. Here we go. And let's check. Now we can define here the offset, so we can fill in those gaps, we can close those gaps. And then of course we can go to the cloner and add more boxes. Here we go, or maybe switch here the seed. Yeah, that's it for this example. So, and maybe for you as an, if you want to do additional stuff, in also my file that I provided, there is some additional stuff in there where you can choose the direction where to stack, if you want to do it in Y, X, Y, or Z, and you can also stack in the negative direction. But this may be also a good exercise for you if you want to do this additional functionality. But I think for now, that's it for this part here. Yes, then I will give it back to you, Noseman. Do we have some questions?
Yeah, not much. First of all, likewise, Jess is going to check out the rest later today, and we are doing well. Thank you very much. And everyone, including Jess, are appreciating your series. And we do have a question from Lisa. She doesn't mind you using Houdini. There's no personal insult taken. But on to the question, how do you decide when to use either Cinema 4D or Houdini? My response would be, if you want to have fun, use Cinema 4D. But what is your response?
For most of my project, I use Cinema 4D because it's super fast, it's super easy. So most of my project, I don't need like super complex stuff. So, but I use Houdini when I need super heavy simulation stuff. So there's some really special thing. So then I jump into Houdini. But actually, when I would say I use my client projects, I use Houdini very, very rarely. So because for most stuff, it's cinema, I'm super fast. I can iterate over different style frames and proof of concept. I'm way faster in cinema than in Houdini. I think Houdini makes more sense when you also work in special effects, and I'm working more in motion design. So I think for motion design, 3D motion design, I totally can recommend go with cinema. But sometimes you need Houdini for some special things. Yeah.
Fantastic. Nothing else for the time being. So, yeah, let's keep going.
Okay, great. So this was the second example, and in the next example, we go try out the second node that I already described. This is the memory node. So here we built this little extrusion solver. So this is super simple. Let me show a little video first, how this will look. So this is super simple. So just extruding on the same geometry and build those kind of, I don't know, scaffold looking effect here. Oh, this is pretty easy, but it explains very good where you can use the memory node. So we can use the memory node as kind of a solver to build those simulation type things. So let's close this. Let's jump into Cinema again. Let's build this from scratch. Let's make a new file. Oops. And we start with a cube. Let's make this smaller. 10 by 10 by 10. Great. And then bring this cube again into nodes. So let's use a nodes mesh. put the cube on the nodes mesh. Let's open it. Maybe let's call this extruder, something like this. Then bring in our child object, same as we did before. Add input, object child. And here we have the geometry and everything. So, and what we like to do is to extrude randomly, so pick randomly a polygon, and then we extrude on those polygons. Let me show you what I mean. So let's pick first a random side. So use a random selection. Plug this in here. And now we like to select, maybe with a lower chance here, select a random polygon. And then let's extrude. So extrude this. Now we can see we extruded maybe also 10. So we extruded it here randomly. So, and if we would do this again and again, so we can copy this and again. Oops, come on. Here we go. So we get this kind of effect. So we go from this to this to this, and then we get this kind of extrusion simulation. But of course, we don't want to chain endless of those those two nodes. We like to do this inside of a memory node, because we want to do this depending on our time. Here, when we press play on every frame, we will do this effect. So we can, for this, we can use the memory node. So let's bring in the memory node. Memory. So this looks pretty similar to the loop carried value, because it does a pretty similar thing. So when we bring in the loop carried value, so as I explained here, the loop carried value, we can define here with the curly brackets how many loops we like to have. So, and do on every loop, we do something iteratively and update the values. The same we can do with the memory, but the memory, we don't have to specify the loops here. The memory does this procedure on every frame. So it updates on every frame. You can already see the difference here. We have here a previous value and the next value. So this is always from the previous frame, and this will be the next value is then from the next frame, and so on. So you will see when we start to build here our setup. So let's delete this one here. So let's take those two nodes here, then dive into the memory. First, we also like to have a geometry here. You see the initial value here is a vector here. So let's switch this to geometry. So bring in here our initial geometry. Let's dive in. Let's paste here our two nodes, the random selection and the extrude. Then plug in here our geometry and this to the output. And now on the random selection, let's make a very low chance here. And let's go outside, and then let's check what we have. So delete those and then plug in the previous first. And you can see the previous is our initial geometry here. So before we do this extrusion, and the next is, you see, after the extrusion here. So when we go to the next frame here, you can see it, we start to extrude. So maybe let's go back. I think we have to add a very low chance here. So let's zoom out. Let's press play. And we can already see we start to get this effect. That's why we, on every frame, we extrude on our random selection, and because the random selection is here very low, this chance, but we get always more geometry. So sometimes a polygon get added to our with the chance to our polygons. So that's why we are adding more polygons to our random selection, and that's where we start to build this effect. So that's already it here, but it would be nice to have some colors here. So let's go outside. So first we need, because we like to do the color with a vertex map, let's add a vertex map first. So we can do this simply with a set color. So this is the easy way. So use a set color. So we have an initial vertex map, and you can see here already we have here a vertex map. So at the moment this is set to random, I think. So on polygons, that's fine. And here, because it doesn't matter at the start, we can change the mode to value. So we can define the color here. Maybe let's also make a material so we can see our color here. Let's add the vertex attribute. Bring in here our, our vertex color, plug this in here. Then the color onto our extruder. Let's close this, go back in here. And now, because we like to, let's go in, we like to change the vertex map over time. That's, so we need first a time node, of course. So import a time. And then we like to set the color in here. So you also need a set color. Set color. So we like to set the color always here of our default selections, or always that thing we like to select. And because we're working on polygons, it's the type is polygon, but we like to color points. So always there's a, on the selected polygons, we like to color the points, and then the value here also, we can define now the value. So let's expose this. And now, because we want to change this over time, first let's grab a gradient first. So gradient, there is this node called basic gradient, where we can choose our gradient, maybe supersonic here. And now here the position, we can define the position. So the position is here from 0. This node is 0. This node is 1. And now we have 100 frames. So we have to map those 100 frames from 0 to 1. So we can do this with a range mapper. Range mapper. So our input is are the frames here. So, and we like to from frame 0 to 100, we map this from 0 to 1. So great, plug this into the position, this into the value, and then let's check. And here we go. Now we have a vertex map according to our frames here, and for this gradient, and the gradient, of course, let's bring this outside here. So we have this as a parameter on our extruder, and then I think that's already it for this example. And there is a good example where you can use the memory node, and the people that know me on my YouTube channel, I use the memory node a lot, especially for stuff like this. So we can solve building kind of our own solver. We can do a lot with this. And in the last example, I show you a little bit what you can do also with the memory, and not just solving. So this will be then in the last example, but then I think first let's ask if there are some additional questions.
Let's quickly, so there is a question, Aymar, can I use node as effector and cloner? And the answer is no. That's it. You can modify geometries. There is a workflow, the op workflow, which we're not really going to see, which allows you to generate objects. We'll see because it's experimental. We're not going to touch upon it, but nothing else. Only geometry parameters. So vertex maps, vertex colors, polygon selections, point positions, and stuff like that, point counts, and so forth. There's nothing we can do directly to MoGraph. So that's number one. Second question that relates to the previous is what if we rotate the objects in Z axis or X axis in the stacking example? Yeah,
Yeah, I can show you. Of course, because the let's rotate it so you can see. Let's add some additional rotation here, and you can see they still are stacked, but because it's better when we see it from the side here. Oops. Because from this box now we have here the maximum bound is now this corner and the minimum bound is this corner. So they look like they are floating or falling apart. So that's when you also add some random rotation in the pitch and the banking. Yeah.
What I would say is you could make them touch better, but you will need to add more programmatic things. For example, use ray casting, project array, find for the same vertical or something like that, the points where the two boxes meet or something like that. You can do a sampling of many points and find which ones are the most probable where the boxes will touch. In general, what I would like to advise everyone, when Dominik started showing how this example was working, he drew out the graph in from the side view. Always figure out what the problem is and how you are intending of solving it on paper, first of all, or using some sort of method that doesn't require programming first. And if you go back a few of our series, when Dominik was showing, I think it was the first series, Dominik, where you were showing how to make the avoidance of the spheres. The
second one, yeah.
Yeah. So Dominik first showed a two-dimensional drawing, a schematic of what the logic was going to be. You have to do that. It's extremely difficult to figure out what's going on in situations like these unless you visualize the problem first. And what Dominik is showing now on the screen is why this is problematic, because you can see that the bounding box, which is always orthogonal to the world, if the two bounding boxes are touching, that doesn't mean the geometry inside them is touching. Okay, so that should be pretty obvious, but always work on a piece of paper. Okay, next question. Can the memory node handle things like every X number of frames?
Of course, yeah, of course. So just have to define it when to. You can do this with a statement, with a comparison. So you always can compare the frame and say each. So you can use a modulo where you say, okay, on every 10th frame do this. So and then on the other frames do nothing. So it's no problem. Yeah.
There is a little hack where you can use a loop carried value. So loop carried value and memory node, they have a bit of an overlap in terms of how the fundamental things work. It's they can recycle whatever's generated in every pass, whatever that pass is, and you can add numbers like here in the stacking example. You're actually adding up and creating a bigger and bigger array from the previous cycle. That's why it's called loop carried value, because you get the value that's being calculated at the end and you carry it back to the beginning and it loops around and around. The memory node does the same thing, but using the animation time. What you could do, you can have a loop carried value that is driven by a time node to do something very specific and similar to memory node. It's not 100% overlap, but it may allow you to do things easier when you say instead of every 5 frames, you put a time node with frames and you divide that by 5. you turn it into an integer, and that means you're going to increase by 1 every 5 frames, and that's going to add whatever the loop carried value does. So there are many ways to do these kind of things, whether directly or indirectly. And I would suggest everyone to experiment with these things. The other question is it possible to export scenes as Alembic files?
Of course,
Yep.
yes.
It's a normal object. Everything.
You can right click and then bake as Alembic. So because at the end it's also just geometry. Like if you like to bake something else, another rigged animation or something, it's the same. Yeah. Because when you say current state object here, see at the end it's just geometry, and you can bake this on each frame, and then you have it as an Alembic, of course. Yes.
So I want to show this, although this is part of a huge conversation. I'm personally against the adoption of artificial intelligence. If you have ever met a public servant that does not care about your individual case and always replies saying, but the regulation says this, and that is AI if you raise it in the 1,000th degree. So I would say, as much as you can, reject it. Now, most people are not rejecting it, so it's becoming more and more part of our lives. My prediction is there's going to be I'm going to keep it very, very simple. I talked about this a few years ago on a panel, and Chris Smith disagreed with me. But I think that I have a point. Things are going to start looking very AI-ish in a few years, because if the majority of images that are created are assisted by AI, we are going to start converging into some sort of look where now we know that look. Okay. I would say that humans still have a future in the realm of arts, and that's because they can think independently of what some geek in a basement told them to think about. So your obligation as humans is to stop feeding the beast with information, especially human information that is, more human-centric, things that machines cannot do and humans can only do. That's number one. Number two, keep working on your craft, because despite what the machine can do, other than recalling things, humans can do a better job. And if not a better job, at least more entertaining, fun, and engaging job. I would say hang in there, expand your expertise. Me as a teacher, it's not even close yet. Just go and ask questions about how to use Cinema 4D, and the amount of idiocy you'll see artificial intelligence is going to tell you to do is just have fun with it. Go ask very specific questions on how things work as a human would ask them, and AI cannot deal with that. And don't teach the machine how to ask these questions. What is your opinion on this?
Yeah, for me, pretty simple. AI is a tool, not an art director. So at the end, you stay the art director. Even you work with AI tools, at the end, it needs an art director to direct stuff. So that's something that AI can't do. So it's also a lot of people that are super good in those generating AI images, but at the end, they struggle when the art director comes and say, can you maybe change this or put this little bit this? And then the AI, then they start to struggle with AI. So yeah, but as tools, that's perfect. So we use this sometimes when you think of all the cool Photoshop tools, so where you can paint out, and so this is very, very, it's a nice lifesaver. So you save a lot of time in terms of rotoscoping and stuff. So it takes the tedious, unpleasant jobs of working in visual effects and stuff, makes this stuff easier, and then keep the creative stuff for you.
Don't write stories. I would say, beautiful stories like Star Wars and all these things that have touched our lives and all that. Machines cannot do it. They can copy. Of course they can copy. They can come up with some sort of concoction, but AI doesn't exist without human input. That's what we always need to remember, right? Zero, absolutely zero. Whereas humans have created everything. If you go back far enough, 2 million years ago, from scratch, right? We created it. We human. No one gave it to us. So machines are inferior. We should treat them as such and make fun of AI as much as possible. Um, what was the next one here? Oh, and the last thing I want to add to this, Jason. Uh, you're all artists, right? Learn how to use your hands. Don't keep drawing on paper. Keep using a good soft pencil and an eraser, a nice rubber eraser, and do your little sculpts using clay and all that, and do your make your stuff using wood and all that, because that's never going to change. All right, doing things with your hand, and the less people are doing it, the more valuable handmade things are going to be. You will find, NFTs had a life cycle of 1 year where everything blew up. I even sold an NFT. Um, uh, but the things that are, you can hold, and things that are handmade are always hold the price and are very worth their value. Anything on that, Dominic?
No, I was very poetic, so I don't have to add.
Agree. Yeah. Let's see another question now. Is it possible to do the same grow effect with spline and limit it to the inside of geometry with specific angle? I know it's possible particle nodes, but just wondering if it's possible. Are you talking about the other one, that the extruding?
Okay. Yeah, I think definitely possible, but you can't extrude actually a spline, so you have to do it in another way. But of course, you can grow splines. So also when you, I think I did I a tutorial about spline growing? Not 100% sure, but of course,
do it anyway,
yeah.
And by the way, don't forget, do I have your link here? Paste me your link to your YouTube channel. I thought put it in the private chat, or go to the comments and just write down your YouTube channel, because Dominic has done, besides this series and all that, he has his own fantastic YouTube channel. Please go subscribe and enable notifications and all that, and comment, because he's done a ton of stuff on his YouTube channel that shows even more stuff than we have here.
Yes.
Yeah, yes, Lisa has already bookmarked it. Let's go back to the question. So yeah, many things are possible. So go and check out Dominic's channel for more information. Drake, my friend, how are you? A question. Tag on question to the current XYZ axis. Question: if we want a cloner setup to grid instead of linear Y, how to adjust the get element node build array? I think what Dominic has done in this setup is he assumes that each and every one of the modeled boxes is a single polygon island. If each one of the box was made out of multiple objects, then we would have a problem separating each other using this method.
Yes.
I don't even think
you can, of course, but then you have to import the stuff in a different way, not with a clone. So you can build on, when you go here to the inputs. So there is the object child and object link, but here at the bottom there is also object children and object links. So you can input multiple objects. So when you use an object link, you see they have then an array. So here you have an object link field, so you can plug in your object in here and then iterate over them. So this is a solution. I used it also in the past. So when your objects are not a single geometry object, if your objects are built with different geometries, then you can plug them into here, or of course you can also plug in them as children and then use the object children part. And
the one thing is, if each object is more than one polygon island, you'll run into the same problem you have with the fracture object, where it either explodes object by object, where you have the object as one object, and this is, you can do that with the children, but if you want to go by, automatically splitting it, the fracture object does not know if you go with explode segments. It will just take every polygon island as a different object. So this is not a nodes limitation. You have to work around it the same way you would do in classic Cinema 4D.
Yes.
So in this particular case, I would assume that if Dominik had an XYZ grid, then each object will just go and center itself. I think you can actually do that. Just set your objects as a grid, and it won't change anything because you are setting the final positions of the objects. Is that correct?
I just offsetted them, so
Okay, there you go.
you're right. It's actually it's a transformation. So maybe let's check to.
Yeah, just make it grid and put 311. So what's happening there?
Yeah, let's make here X, Y, maybe this, yeah, 311. Let's check. So yeah, at the end we just offset them. So yeah, they stay at the same point here. Yeah, of course, because we don't, we just offset them in the Y direction. We don't set the position, so we have to do it in a little bit something different. But because we, at the end, we just transform the geometry.
Yeah, what I would do is center the geometry using a geometry center, and then just transform the Y. So there are ways to do it depending on what you want. In this particular case, the Ys are aligned, but the X's and Z's are not. So you get the same X and Z, and you just align the Ys. Again, programmatically, you could do whatever you want. Let's see if that's going to work now.
This should work. There should stay. Yeah.
Do that. There you go. So here, what Dominik did with the geometry axes is it just resets the points of the object, because the axis never moves, even in Cinema 4D. What moves is the points relative to the axis.
Yes.
And then it aligns everything on 0, 0 and takes only the Y and stacks it up. Hope this answers the question.
Yeah.
And of course, good, what time is it here? Oh, it's good afternoon here, and good evening in Switzerland.
It's 7:15 here.
So quickly,
already dark.
would rigid body break the node for the stacking? Well, rigid bodies take over. If you put a rigid body tag, they should just fall on each other, because Cinema 4D does not have any effect on the objects after the simulation has been initiated. I would assume. So that would work.
Should work here, yeah. I think. I'm not sure if you have to split it up first, but not 100% sure what will happen. Not a cube. Bring in a plane. So, and
is it a single object? No, it's going to be a single object, right?
I think so. Yeah. Yeah.
Yeah. So you need to put it under a fracture object to get the objects back, and then that will be it pretty much.
Yeah.
Okay. This is homework for Gerald. Okay, Gerald, your homework for if you wish to accept this mission is to try that.
Yeah.
And the files are available anyway, so we shouldn't have any problem. Quickly, let's see if we have any other question. The bigger issue with AI is humans are giving it too much information. Come on, that's the problem. If no one gave it information, the only way they could do it is only steal. That's it. And that will be easier to tackle. Okay, no more AI questions. We need to have a summit on what do we think about AI. There you go, Phil. Question, what does it say here? Is it possible export C nodes? Yes. Yep, that was a reply to the question. Thank you very much, Artem. And yep, your homework, Dean. You just set yourself up. Okay, let's see quickly. two things. Thanks for finishing out the actual question intended from the type, and thanks Dominic for the object, children and links. And yeah, we are. I'm going to reference these in the upcoming tutorials. So the more you ask questions, the more I know what to show. Yes, we have enjoyed it, Phil, doing it as well. Okay. Let's go. The floor is yours. Do you have anything else to show us, Dominic?
Yeah, I have a last one. So I think we're a bit over time, but this is normal. So last one where I show you also how you can use the memory node. So let's jump into the presentation here. And yeah, as I said, this looks a bit boring, but it could be very useful because I built this actually because of a question of one of my followers. So he asked if it is possible to attach an object to the closest point where it lives in the scene, and then if it is possible to stay on this point. So maybe let's open the file and you see what I mean. Where is it? Let's go to cinema. Yes. Maybe let's remove this one here. So you can see here we have this cone here. So maybe let's add snapping so we can place the cone here. So it snaps always to the closest point. And now the sphere is moving. I think it's rotate, and the mesh is also deforming. So, but now this cone will stay here on this point. So this is something where we can also use the node. The memory node. So we go back here. I can again maybe place it here. So, and now it will stay. It works kind of like a constraint. So maybe if you want to attach a clock to a moving mesh or something, it's always search the closest point where it lives in the scene, and then it stays there. So that's what we gonna build. So I made here a little starter scene. So I think it's this one. Yes, so here we inside the scene. So we have the sphere here again. You can already see also that the sphere is placed not in the center of the world. So it is a little bit offsetted here and also a little bit rotated. Then the same will be here for our cone. So we maybe start here with the cone and we place it here, maybe here, and then maybe rotate it. So we have here messed up positions and rotations, and here too. So that's something we also have to deal with if we want to build a robust system. So we do a little bit of matrix transformation. So I hope this helps also a bit, because it's something that you normally need a lot when you work with node stuff. You know how to deal with matrices. So then I think let's jump in and let's build this as a modifier. So we can add this as a modifier to all our objects that we have, and then all our object that has this modifier will stick to the closest point, and then it will stay there no matter where are we in the where we are in the timeline. So let's go back. Maybe let's place it again here for start point, maybe around here. So this one is the closest point here. Then let's add a modifier here. Let's search for nodes. And now we add not a nodes mesh. We like to add a nodes modifier. So bring this in here. Let's open it. So and then I have to open my little cheat sheet, of course. So go on. Here we go. So so first thing we have to do is to find the closest point first. So so for this we need inside our nodes modifier. Here we have the geometry of the cone, but we also need the geometry of our wobbling sphere here. So this time we like to use not the object child, we like to use the object link. So when we click now here, we have here under the inputs an object link where we can place here our sphere. So then we have here the geometry of our sphere. And you can see here in the nodes modifier, we have a lot of those different matrices. So we have the capsule matrix. So this is the matrix of the actual capsule here. And you have the local object matrix and the global object matrix, then the local capsule matrix. But what we need is actually the global object matrix of our object that we are modifying, so of the cone. So those values here, and they are live in here in the global object matrix. In this matrix, we have all this information. So let's search for the closest point here. So let's use a closest point node for this. So say closest points. And then we like to search on our sphere. And the query position, we can directly plug in the global object matrix into our query position. Then you can see we have here this little dot. That means it converts the object matrix into a position, so into a vector. And now we have here the closest indices. So maybe let's check if this worked. Let's bring this over here. Let's first, on the closest point, of course, we have to set the maximum distance here. So let's make a high distance, so it always finds the mesh. And then we need just one neighbor, so we just need one point. And then here we like to search on all points, on the whole mesh. And then let's get the found indices here. So get element. Then we have here the value, and now we want to check this value, so we can use a text for this, just to check the value here. So then we have a text here, and for inside of the text spline, we can plug into here and then bring this out here, and now we can check here the value. So right click, then port inspector. And then here's 192. Now let's check if this is correct. So this point should be 192. I'll go to the sphere, go to points, then display, then say polygon point indices. And now let's check, and we see this is 53. So think, why is this not correct here? That's because our sphere here is not in the center, so it has messed up positions here. So that's why we have in here, we're just importing the raw geometry, not the transformed geometry, because here our sphere is transformed by these rotations here and by this position. So we also have to transform inside here. We have to transform our sphere first here. So we have here also the global matrix here of our sphere. So these are these informations here, so position, rotation, and scale. So let's transform geometry, plug in our sphere, use the global matrix, plug this in here. Let's check. Now we have 53. Now this matches. You can see here this indices, this index here is the closest to our cone. So great. So then what we have to do next, let's hide those indices again. Let's place our cone on this point. So we like to place it, so we have to define the position, and also we like to take the normal of this point to align. So the cone maybe at the moment it looks in this direction. Also I like to align the cone on the normal of this point. So when we say here, you can see when we show the normals, polygon vertex normals. So I think we have to convert it so you can see what the normals actually look like. So why are there no normals? Weird. should show the normals, I think. Okay, polygon normals are here. So, yeah, but you can see a normal is also it's pointing outwards here from the polygon, and the points should also show here. The normals, not 100% sure why. Now they show up. Here we go. And these are the point normals. So we like to align our coin along this point normal here. Great. So let's delete this here. Let's dive in. And what we need first is the position of this found point and also the normals. So we can use a node called get geometry property get. So we can also type in just get position. Then we get the geometry property get already predefined with positions. So see it type, we like to search for positions on our sphere geometry. And also we can duplicate this. Also when you duplicate, you can press on Control, so you duplicate the node. When you also press down Shift, you also duplicate the connection here. So, and then we switch this here to normals. So now we make sure that every object has point normals. So we use an generate point normal here. Just plug this in here. So now we make sure we always have point normals here. And now we like to get the corresponding position and the corresponding normal of the found point here. So our point with the index 53. So let's use a get element. Get element. Plug in here our index, and the same here for our normal. And now let's check. Let's get here our geometry and just transform it. So, and what we think of is, okay, when we now plug in here, maybe we delete the text here. When we plug in here our found position of the point index here, 53, plug this into translation, the geometry should go to there, but let's check. You can see this don't work. The geometry is now moving to here. This is, why is this? This is because we are working inside of the space of the cone, and the cone is, when you deactivate the cone, is placed here. So we move the value that we have from this coordinate system, we move the cone. So that's not what we want. We actually want to move from the center. And there is where, a very handy solution we can do. There's something that you normally use a lot when you work with geometry. You have to inverse your object first. So the object is always in the center. So maybe let me show this. First, let's make a display so we can see through the sphere here. And now we use an inverse matrix, is this called? Inverse matrix. It's this one. And we want the inverse matrix of our global object matrix. So from the cone, so from this one, we want the inverse matrix. So you will see what this will do. You don't have to understand it 100%. It's just super handy, the inverse matrix. When you now transform here our geometry with the inverse matrix. Oh. So we have to activate it, of course. You can see we always bring the geometry back to the zero coordinate of our world coordinate system. So it doesn't matter where the cone is. So we can move this around here. It doesn't matter, and we can rotate. It always brings it back here to the center. So this is great. So because it is in the center, we can move it now by here our position that we found, and of course also align it by our normal that we found here. So great. So maybe let's bring this back here. So we are at this point 53. So let's Yeah, now it is transformed to the bottom. We could do it with another transform, but we can combine matrices. So we have here our inverse matrix that brings it back. And now we can combine this with another matrix. So we have transform matrix here. So matrices. So we can combine matrices together. So we use our inverse matrix. And then in the second matrix, we like to use the translation, and then we use this matrix here to the transform here, and now we can see it is placed exactly on the point that we like. So great. And now we also need the direction, so to align along the normal. So we have here the normal. So we can't plug in this directly into the rotation. We have to first build a rotation matrix. So there is a handy node called alignment. So this one here. So at this one, we can say the axis is the Z axis. So because our cone, so when you don't deactivate here and reset the cone here, you can see the cone looks into the Z direction. So we like to align the Z direction along our normal. So the normal here will be our direction, and the alignment is the Z direction. So let's activate this again, and then open the matrix here, and then we get the rotation here. Here we go. And now, because it's here at the bottom, we can now bring this back here. So let's zoom out. Then let's maybe activate the snapping, take our cone, and then you can see maybe deactivate this one, display tag again. And now we can snap to each point here, and it will stay there. So on frame 0, so great. This is close. We are close to the finish. So, but now when we press play, you can see it starts to jump around, because when the geometry is rotating and moving around, of course, the closest point is also changing. So we need a solution to store the initial point on frame 0. So this is pretty easy. So where we have here our initial index, we can plug in here a memory node. Here's a memory. Then say the initial value is an integer, so our index of our closest point. Plug this into the initial, then dive into the memory node, and just plug the initial here to the next. So, and this will make sure that it will stay always the same value here. So we can now plug them into the previous here or to the next, doesn't matter actually. Now we can press play, and it will stay always at the first found point. So maybe we can check here by like port inspector. You see this actually changes, but because we store with the memory node, we stored it on the frame 0. So also port inspector. So you can see this one changes, but here we stored the first found point, and now our geometry will stay always on this point. And then of course, let's go back, and then we can say, just move it around, place it maybe here or down here. Okay. Let's press play, and it will always stay there. So we built kind of a little constraint modifier, so where we can always make sure that the object will always stay at the closest point.
Fantastic. Yeah, there's one question from Lisa, which is actually quite interesting, and will show something. If the cone is attached to a hierarchy, will all the objects be affected? So I would suggest add a sphere and make them siblings and put everything under a null, and everything should go
because we use the global matrix, so it doesn't matter. Yeah, maybe we have to maybe move this around here. So, and also those objects doesn't matter. So we can also use another null and place the cone in there. So because we use the global matrix, so it doesn't matter how the hierarchy looks like. So it always take the global position. So as said here, you have here the global object matrix from our cone and also the global object matrix of our sphere. So the hierarchy doesn't matter. So this is where we had
something else.
Okay, sorry.
So in the object manager,
Mhm.
put your modifier as a sibling of the cone. So just drag it up,
Yeah,
and
of
then
course.
go and add a sphere with the cone as brothers.
Yes. So let's bring in a little sphere. Put them in here.
There you go.
Here we
And it
go.
shall work.
Should work. Oh, maybe we have to go to the first frame, of course.
Yep.
So let's take the sphere here, place the sphere here, and the cone's there.
There you go.
No, it jumps to the same. Should actually work as individual object. That's funny.
Interesting.
Yeah.
Oh, it's because you have the memory node. It's a memory for, and it will keep that number.
Yeah. We have to
okay, so
duplicate it. I think.
They will both move to the same point. But if you want the two objects to be there, you just have to do some.
Yeah, you have to duplicate because every object needs its own memory node because they have individual indices. So the closest point they have to have. We need two memory nodes, so every memory node can save the closest point for each object here.
I misunderstood the question. Yeah, make the sphere a child of the cone. It will treat them as two objects. What you're seeing now, when you have more than one objects as, oops, it's a wrong one here. I will. Yeah, it's just like applying a deformer on more than one object. It's just going to go and apply the deformer to all the objects. It's not that the cone is going to drag the sphere with it. And don't forget that C nodes are not moving the object position. They are moving the point positions. That's a very, very important distinction. There was a question about Expresso earlier. Expresso being an expression editor, you can tell Expresso to change the matrix of an object. Using C nodes as we've been using it doesn't allow you to do that. You can generate objects in various positions in the with different matrices using the op, but that's a different story. But essentially, C nodes is predominantly made to deal with points, moving points around. You're not moving the matrices around. So always remember that. Excellent. And does that conclude our day today?
Yes, that's it.
Only you overrun only by 43 minutes.
Actually, I thought now in all the other streams I added additional examples because I thought maybe if we have enough time I can show some additional stuff. But I knew already from the other streams you don't have enough time, so I just showed those 3 or 4 examples and left the other stuff. Yeah.
Yeah, Lisa is asking, can she stop by your studio with a laptop? Yeah, Switzerland, I guess. Anyway, I would like to remind people that go check out the download links or use the download links you already got an email for, because if there are any new files added, you're going to find them in there. But in any case, first of all, I would like to thank Dominik for sharing his wisdom and knowledge with us. And, with popular demand, maybe Dominik can join us again. He is close to Maxon anyway, so we have the privilege of talking to Dominik whenever we want. But you get him whenever he decides to go live.
Yeah.
Go watch his YouTube
Yeah,
videos,
yeah.
ask any questions there. And thanks to all our viewers for being with us these 5 weeks, 4 with Dominik and 1 with myself and Jonas. And the Node saga has just begun. So, it's here to stay for a while. And yeah, thank you, everyone. Thanks, Dominik.
Thank you. Thank you too.
And I need to find all those videos. I always say this in the end because I get carried away by the discussion. And I need to remember, what do I need to... Oh, there you go. I think it's the thing over there. And there's a QR code as well for everyone. Bye-bye.
Bye-bye. Thank you. Bye-bye.